In this lecture, we'll look at input and output distance functions, also look at some empirical applications and what we need to apply them. An input distance function simply translates a given vector of n inputs and m outputs into an input distance function value, and that value can be a non-negative number or positive infinity. And we'll explain what that is, but before we go there, let's first just take a simple example. Something familiar, a production process where we use two inputs and we have an isoquant for producing, say, a given output y, and we have an observation where a producer is using a vector x1 0, x2 0, let's say, to produce y. Given this point, we know that the input combinations we are using or the input levels are beyond what we need. Actually, what we need is a smaller input set, which could be b on the boundary if we think in terms of proportionally shrinking the input vector we are using. Let's denote the origin by O, and we know that the efficiency of this point A is actually equal to the minimum input we need divided by the actual input we are using. So if we think of the minimum input required divided by actual input, well, we know we could shrink A proportionally towards B and still produce the output Y. So our technical efficiency is simply OB over OA. We know that. Now, what does the input distance function represent? Well, the input distance function represents the same concept, but it's defined in the inverse, in the sense that we are looking for a number, theta, that we can shrink our input vector by, scale it by, and still be able to produce y. So we are looking for a factor theta, the maximum factor theta, that we could deflate our input vector by and still be able to produce y, which means y and the deflated vector are still within the technology set. And that number is our distance function value. Well, if we go back here and look at what that number should be, what's the maximum factor by which we could deflate our input vector A and still be able to produce y? Well, that factor is the inverse of our efficiency measure here, and that factor is the distance function value at this point would be equal to the maximum amount or supremum theta, such that y and x1 divided by theta and x2 naught divided by theta is still feasible. And that number obviously is, if we are thinking of theta, then theta is, well, dividing both input vector values by the same factor, and that number is going to be OA over OB. So the distance function value, which gives us the maximum factor by which we could shrink our input vector and still be able to produce y, is the inverse of our efficiency measure. So we can simply write TE equals 1 over the distance function value in this case. So the mathematical definition we have here is a formal expression of what a distance function value is, but it's something that we have been already doing when we do think of DA and so on, and we are defining the technical efficiency as a ratio of the minimum to the actual input use. So that's the definition of a distance function. It can be refined, but the intuition, as I just said, is the value of the input distance function measures the maximum factor by which the input vector can be proportionally deflated or scaled down given the output vector and the state of the technology. And other distance function can be defined similarly, but we'll come back to this later. So let's say we have a production function which is given by this cubic function. Let's say we have an observed point A where we are using 60 units of X to produce 68 units of Y. And obviously, because this point is below the production function frontier, it's inefficient, but that inefficiency in this case is being measured in terms of input orientation. So we don't look how far we are vertically. Instead, we look at how far we are from the frontier horizontally. So to measure efficiency in an input-oriented sense, which is what the input distance function does, we look at how far we are from the frontier horizontally. Now, if we look at the frontier, it's telling us we could have used only 40 instead of 60 units of the input, and therefore our input distance function is going to be given by AC over BC, and that's 1.5, which is 60 over 40, which if we had been defining technical efficiency, we would have said, well, technical efficiency is the minimum input we need, which is 40, divided by the actual input, which is 60, and that's simply 1 over the distance function value, which is 1 over 1.5, or roughly 2 over 3, which is about 0.67. Okay. And if we have an isoquant, let's say we have a Cobb-Douglas production function, y is a function of labor and capital. And for an output level, y equals 30, we can draw an isoquant. And suppose we have an input combination that's observed, and that input combination is at point A, labor equals 50 and capital equals 60. Obviously, that input combination is inefficient because we can see that we could do with a smaller input set, which is about 40 units of labor and 48 units of capital. So what's our input distance function? Well, our input distance function, again, here is the maximum factor by which we could deflate the input vector A and still produce 30 units of output, but that is simply a maximum factor by which we need to deflate A to bring it down to B, and that's going to be the ratio of the inputs at A to the inputs at B. And for labor, for example, that's 50 divided by 40.32, and that's 1.24. So our input distance function is 1.24. So let's get closer to how Shepard defines the input distance function by covering a few more cases. So what's the input distance function value for points such as A, C, and E? A is similar to what we have been doing, so we know what that is. At point A, the input distance function is going to be OA over OB. So that's easy. What is the input distance function going to be at point C? So if we look at the isoquant now, the isoquant for producing output Y joins the Y-axis. So if we look at here, point D, we see that if you are using only x2 and 0 amounts of x1, you could produce Y, because there is a point on the y-axis where it is possible to produce y. You just need to use the amount of x2 indicated at point D. Therefore, if we look at point C, the input distance function would be the maximum factor by which we deflate this input vector at C and be able to produce y, or still be able to produce y. Well, now point C cannot produce y because it's below the isoquant and it's not feasible to produce y using C. There isn't enough input in C to produce y. Therefore, when we are dividing C so that we can bring it to a level proportionally scaling where we can produce y, then it would have to be scaled up. So the theta factor, the maximum amount by which we divide the input vector at C, would have to be a fraction, so that the scaled up or deflated factor, in fact, is bigger than C. So how much bigger should it be? Well, we should be able to bring C to point D. But to do that, the deflation factor should be the maximum theta, such that the input vector at C is able to produce y. But that factor is going to be simply a scaling, so that point C comes up to point D. And what that means in simple terms is, well, it will have to be the amount of x2 at point D divided by the amount of x2 at point C. And that's our distance function value. So if we just use the levels C and D to measure distance, then we could just say that's going to be OD over OC, just looking at the distances from the origin. So for point C, the input distance function is defined. For point A, the input distance function is defined. Now let's look at another point on the boundary, point E. Now, as you can see, the isoquant for producing y does not touch or intersect the x-axis. So it's telling us that there is no way to produce y without using x2. Doesn't matter how much x1 you have, x2 is essential to producing y. Therefore, point E, which has a zero amount of x2, even if you scale it by a fraction, no matter how small that fraction is, which means even if you scale it, no matter how big that scaling is, there is no way that you can scale it to a level where you can produce y. Therefore, the input distance function at point E would have to be something that requires deflation by zero, which means you are scaling up the input vector to infinity, but that's simply to say that you cannot use that input vector, no matter how high it's scaled, to produce y. So it's useful to define or identify some of the segments of the domain of input vectors, so that we can define the distance function much more clearly. One is the origin, where there is no inputs. Second is the set of all interior points, meaning the inputs are all positive. And the third is boundary points, where one or more of the inputs could be zero. So the boundary points can be simply defined as the set of points x, where if you were to multiply the input vectors, they would be zero. Product would be zero because one of them at least is zero. And we can distinguish between two subsets of boundary points. There are two types of boundary points. One is the set of points that are similar to what we were looking at previously as point C, that could be scaled up to become feasible for producing y. And the other one is the set of points like E, where there is no scaling that you could do to be able to produce y. So these two subsegments of the boundary points are the set of points like point C in the previous slide, where you can get a scaling factor and they can be scaled up to be members of the input requirement set after scaling. So that means if you project them away from the origin, then they would be big enough to become members of the input requirement set. The other subset of points is the points like E, where there is no scaling. There is no factor lambda by which you could scale them up to make them members of the input requirement set. So such points are points where they are missing an essential input, and because they are missing an essential input, there is no amount of scaling that you can do to turn them into points that are capable of producing y. So what do these subsets mean for defining the input distance function? Well, if you have points that can be scaled up to become feasible or capable of producing y, then the distance function value is a positive and finite number. So if the input vector we are looking at is either an interior point or a boundary point, like C in the previous slide, then the input distance function is well defined and it has a finite positive value. So if we are looking at points in here or something like point C, where it can be scaled up to become a member of the input requirement set for Y, then the distance function is well defined because we can figure out a finite positive number by which we should scale up the input vector to bring it to the boundary for the input requirement set for Y. And that distance function value is simply the norm of the actual input vector divided by the norm of the input vector xi, where xi is a scaled version of the input vector. So, and the amount of scaling we need to bring x to xi is, well, the minimum lambda by which we need to shrink or scale down our x vector so that it's still a member of the input requirement set. So that's the input distance function, and in most cases that's what applies, because when we are looking at points, there will be points that have been observed in practice. So x is a feasible point, it has been observed in practice, meaning it's part of the technology, but it's not efficient because it's using excess inputs. And then usually we are thinking in terms of how much to shrink the input vector by to bring it to the boundary of the technology. And in those cases, the input distance function is a positive finite value. And if we have a case where we had like point E in the previous slide, and we have an input requirement set that never touches the x-axis, for example here x1, there is no amount of scaling that we can apply to E to bring it to the frontier for the input requirement set Y, or the isoquant for Y. In that case, the input distance function is 0. It is the same if we have an input vector that's 0 or null, meaning that there is no input in our vector, and then there is no way you could scale that up. And to indicate that there is no amount of scaling you can apply to it, we define the distance function value as 0, meaning that we are scaling it up to infinity, basically showing that it's not possible. The last case we need to look at is when the output is 0. If the output is 0, then assuming that we don't need any inputs to produce nothing, then the distance function value is infinity, meaning whatever input set we have to divide it by infinity to turn it into a null vector. So that's how we define a distance function. It's very easy, and if you have the points drawn, it's easy to show graphically what it is. So if we have points like point A here in the middle, and you know that the projection towards the origin cuts the isoquant at B, and you have a point C here like we were looking at before, and the isoquant cuts the y-axis at D. So in cases like A and C, it's easy to define what the distance function is. It's if we take the origin as O, OA over OB for A, and OD over OC for point C. But if we have points like E on the x1 axis, and the isoquant never touches the x1 axis, then the input distance function value at this point is going to be 0, indicating that you need to inflate it to infinity to be able to make it feasible. But that's just simply a formal way of saying that there is no amount of scaling that you can apply to E to bring it to the input requirement set for Y. Okay, another point to look at is what the distance function values being greater or less than 1 or equal to 1 indicate. In points such as A and C, the distance function values are different from 1. At point A, the distance function value is above 1, meaning that we need to scale down our inputs to bring it to the frontier. But at point C, which is too small to produce Y, the input distance function is below 1, meaning we need to scale it up, not down, to bring it to the frontier. So we need to scale it to bring it to D. And at points such as E, it's 0. Of course, that has been explained already. So this is important to remember what the distance function value indicates, whether it's above, below, or equal to 1. And if the point is on the boundary or on the isoquant, then the input distance function value will be 1, meaning it's efficient. So it's very easy to see that the distance function has some identifiable properties. One of them is that it has a finite value if the output vector is not null. Another property is that it's non-decreasing and continuous function of x. So if we have two input vectors, x prime and x prime is greater or equal to x, then the distance function value at x prime is bigger or equal to the one at x. Another useful property is linear homogeneity in x, or the input vector, and this simply says if we scale up the input vector by a factor lambda, then the value of the distance function is scaled up by lambda. And this is very useful in terms of estimation as well, as we'll see later. It's also super additive, so the input distance function, if it's evaluated at the sum of two input vectors x and z and a given output vector y, that value is at least as big as the sum of the input distance function value evaluated at each of those vectors separately. So this is what super additive means, and it's also possible to show that the input distance function is a concave function of x. And finally, it's a non-increasing and quasi-concave function of the out vector y. So these are the properties of the distance function. It's important to distinguish between three cases in terms of input-output combinations and what the distance function values mean. For example, if we have an input in vector x and an output vector y, and if the distance function value for that combination is bigger than 1 or equal to 1, then that's telling us that x is at least capable of producing y, or in other words, the combination of inputs and outputs is feasible or is a member of the technology set T. A special case of that is when the distance function value is just 1, equal to 1. This means that the maximum factor by which we could deflate the input vector is 1, which means it's at the boundary of the input requirement set or on the isoquant, and in that sense it's efficient. However, if the distance function value for an input vector x and output vector y is less than 1, that means we need to scale the input vector by a fraction, meaning that it needs to be bigger to be able to produce y. So as it is, x is not capable of producing the output vector y. So it's not possible to produce y with x. Instead, we need to scale it up by dividing by a fraction. And that's what the distance function is telling us. So in terms of log values for the distance function, this translates into the log of d being greater or equal to 0 here, the log of d being equal to exactly 0 in the second case, and in the last case the log of d is below 0, because the log of a number that's smaller than 1 is always negative. This is useful because when we are thinking in terms of functional form, especially the translog for the input distance function, then we have to require that if we have observed data, that the log of the distance function value at those observed data points be non-negative because they are observed, meaning that they are feasible input-output combinations. And in the estimation, if our estimation method allows that, it's useful to impose that so that we add some information into the estimation process which recognizes that the sample is feasible or included in the technology set. Let's now look at the output distance function. So once you know what the input distance function is, it's very easy to think about the output distance function. The input distance function was based on deflating the input vector. The output distance function is based on inflating the output vector. And the inflation is happening by looking for the smallest factor by which you could deflate your output vector. So that's the same thing as finding the smallest theta by which I could divide my output vector is the same thing as finding the maximum lambda by which I could scale it up. So we are talking about scaling up the output vector. And again, it's going to be a function that translates n inputs and a vector of m outputs into a result, which is either a non-negative number or infinity. And that's the output distance function. So that's the output distance function. Look for the minimum factor by which you could proportionally deflate your output vector and still be able to produce it given the state of the production technology. So in other words, the output distance function value is a measure of technical efficiency in the output orientation. So let's say we have a production possibility curve telling us what we could produce in terms of y1 and y2, and this is the PPC for an input vector x, let's say, which is fixed, and I have a point A here, which tells me the combination of y1 and y2 that is produced. Then the output distance function would be measuring the minimum proportion by which this could be deflated and still be producible. And that means I am thinking in terms of projecting A onto B, and the output distance function, OD, would be the minimum theta by which I could divide my theta by, and still the combination of inputs and outputs is feasible. So that is going to be OA over OB. And OA over AB is simply the output-oriented measure of technical efficiency. So that's the output distance function. And if we look at the example we had before for an input distance function, it's a cubic function, and the observed point here is point A, where we are using 60 units of input to produce 68 units of output. But if we look at the production function and point D in particular, it's clear that we could have produced 102 units of output. So in this case, the output distance function is going to be a ratio of the actual output, which is 68, to the maximum output possible, which is 102 and 67. And the fact that we have the same level of efficiency here as we did before is just a coincidence. Input and output oriented measures of efficiency are not always the same unless we have constant returns to scale, which we don't in this case. And thinking of the properties of the output distance function, it's a non-decreasing and continuous function of output, and it's also homogeneous of degree 1 in outputs. It's sub-additive. The input distance function was super-additive. This one is sub-additive, which means if we look at two output vectors, u and v, and a given input vector x, the output distance function at the sum of those output vectors is smaller than the output distance function at u plus the output distance function at v added up. and the output distance function is convex in outputs. It's also quasi-convex and lower semi-continuous in inputs. So these are the properties of the output distance function, and they are important to remember, and when you are doing empirical analysis they are useful. Empirical implementation. So the output and input distance functions are called radial because they are based on scaling of inputs or outputs. For empirical implementation, it's necessary to remember some of the properties, and especially those that can be easily imposed globally, such as homogeneity property. So as in the case of cost and profit functions, which are linear homogeneous in prices, input and output distance functions are linear homogeneous in inputs and outputs respectively. And as in the case of cost and profit functions, there are very easy ways of implementing this property so that it's satisfied by the estimated functions. And imposing this property also means there is some implication for functional form, and in particular we can use a translog to impose the homogeneity property globally, and that means we have to be using the translog if we are doing radial distance functions. And how do we estimate the distance function? We have different alternatives. Early on, when work began on using distance functions in the early 90s, mathematical programming was used because it was easy to impose some of the properties like monotonicity, linear homogeneity obviously, and so on, but not the curvature ones because they tend to be complex. So mathematical programming was used in the 90s, but it's also possible to estimate distance functions using maximum likelihood methods. So when they are estimated using mathematical programming, they are estimated without allowing for noise, so that means as deterministic frontiers. But if maximum likelihood is used, then they can be estimated as stochastic frontiers. Bayesian methods can go a bit further because they can be used to estimate the stochastic frontiers, but also by imposing monotonicity and other properties of the function much more easily than could be done with maximum likelihood. So we have different ways of estimating them. Obviously, in terms of ease of estimation, mathematical programming is easier. The next one in terms of difficulty is maximum likelihood, but it's possible to transform distance functions so that they look like stochastic production frontiers, and this transformation is done by using the linear homogeneity properties. Bayesian estimation is a bit more work, but it's also more useful in terms of the options it provides. So in terms of examples, there is plenty of examples. So there is a paper by Ma and Hailu that uses input distance functions to estimate carbon abatement costs for China, and you can look at that. It's available in the LMS, but there are also many other examples that you could look at. So what does the paper do? It's using data from the provinces in China and looking at their economic activity and their emissions in terms of greenhouse and other air pollutants, and trying to estimate the shadow prices for emission reduction. So it is input distance function, but also estimates other functions such as output and directional distance function. So it's a good empirical application that you could look at as an example. But also we have looked at the example from my work on the Canadian pulp and paper industry. That's another example, which is mathematical programming. There are many other examples in the literature, so there is plenty of examples to look at.